So, the next speaker. Fabio Gramazio is an architect with multidisciplinary interests ranging from the computational design and robotic fabrication to the material innovation. In 2000, he co-founded the architecture practice Gramazio Kohler Architects, where numerous award-winning designs have been realized. Opening the world's first architectural robotic fabrication laboratory at ETH Zurich, Gramazio Kohler's research has been formative in the field of digital architecture, setting precedent and de facto creating a new research field merging advanced architectural design and additive fabrication process through the customized use of industrial robots. With us, Fabio Gramazio.
So, thank you, Filippa. Thank you, Tiago, for the great invitation. It's pretty hard to come after Gilles because I was, very concentrated, and I would have liked to go on discussing with him his provocation, and now I have to, change state of mind and go back to my boring stuff I have presented many times. But anyway. I will talk about the concept of digital materiality. And when I was invited to this conference with the title From High to Low Tech, I was trying to find out how this, let's say our topic would relate to this, because there are two ways to relate to it. Either by saying, okay, you go from low tech to high tech, or from high tech to low tech. So the question is there sort of a priority between these things? Is there an ideological judgment? Is the high tech better than the low tech, or the inverse? It's not a question. I was just, reflecting on it, and I said, no, this is interesting because actually this matches with our point of departure. When almost 20 years ago, the term digital materiality is a bit younger, but it expresses what our discomfort was back then. So having these two realities, the physical one, the architectural one, the analog one, on one side being let's say the reality architecture was discussed back then, at least in our school, a very conservative school, a very, and the digital as being the new thing back then still, being an incredible enabler, for new formal manifestation of architecture, for also a mean to rethink many of these things that failed in 20th century in a complete new perspective and new light. And our point was, or our discomfort was, that these two realities were completely separated. Nobody was caring of bringing these two things together. In the 90s, digital architecture, we have seen a few examples, was a very specific thing, but there was no dialogue whatsoever with the other, let's say the 99% of the architects that were still, in another discourse and context, that would look at the digital as something potentially dangerous, potentially, destabilizing, that could destabilize the laws of architecture. And then we discovered that exactly, if trying to transit from data, so from what was left at the end of the 90s, with the internet and all these things, so 10 years of digitalizing everything. So if you would try to move back into the realm of architecture, we could tie this thing together because they would become dependent to each other. So you could claim that in order to build a new physical architecture, not the virtual architecture, but the physical one, you would need the digital and the machines that could then would be able to read the data and create architecture. So to transit from the digital to the material. Now I would like to show you a very old project. This is not research. Most of the other projects will be research projects. This is a sort of a provocation we did in our office in 2002, 2003. Basically building on this first smartphone. It was not called a smartphone, that was able to run apps that were not called apps. And not even Nokia knew that they could run apps. You know, this was the tragedy of this company. You know, but anyway, we wrote a piece of software because this is what an app allows you. So to write something and put it on another device that doesn't belong to you, that would allow a layman to design a piece of furniture. And we would allow, I'll show you this movie, the user to manipulate a surface by placing points on it and then applying pressure. I mean, with the thumb, because was not a touch screen. This was still a joystick, and with the pressure of the thumb to deform the surface, and the deformation would, of course, through a very simple, geometrical operation, intersect with the other side of the plate, and create a hole. By doing this, we allowed to create extremely complex landscapes, you know, as being the surface of these tables, to somebody without any education in this context, so the layman, while everything stayed compressed in very few, very simple, very minimal parameters that were even human readable. You know, there is clearly an authorship, there is something like a color, then it gets a bit more complex, but still, if you have seen the logic of the design, it's very straightforward. It's XY coordinates and magnitude applied to it. And with this, we are able, if we know the algorithm that created it, so what is then at the end the design, you can generate this very complex NURB surface, and with another step, a fully automatic step of just translating data, you can create or generate G-code that then runs this CNC router, a very simple machine, again, that carves, cuts out, mills out this very complex shape out of a very expensive piece of walnut, you know. And then you end up having such objects which are extremely irritating because they are elegant and at the same time they are questioning everything, you know, the absurd, you know, table with a hole doesn't make sense, sort of, and it's even worse if somebody that doesn't have any design education does it, you know. So basically what we were doing here was to shortcut the act of designing on a device that would not be perceived as, you know, an office machine, but just as, you know, a commodity, a phone. Until a year before, this was just a phone. You could use such a mobile phone to do phone calls. And here we allowed this thing to run an incredibly complex CAD software, you know. And then without any human mediation, you know, just automatically we output on the other side a piece of an incredibly high resolution piece of material that is both beautiful and extremely problematic, you know. And in between there is just a payment. It's just a lot of money, you know, because this stuff is expensive. We're limited to 10, you know. It was the condition in order to be able to do it, but it's like this. And we end up, of course, we ended up with these 10 pieces bought by people that still have them, love them. But the interesting thing is the rest of them. You know, all these tables that were designed and never manufactured for good reasons, probably. And this is just there's a short amount of them that I show here. And if you go through them, you see how different they are. Some are more elegant than others. Some would work structurally, others don't. But most striking then the difference is how similar they are. You know, if you close a bit the eyes, these things are almost identical. And this questions two things. On one side, this myth of, the complete freedom that back then, this was a time of all the configurators online and so on, from sneakers to furniture systems and so on. And here we were radically saying, okay, you're not going to choose just the color and the dimension, in modules. We'll give you the freedom on the form, so you can mess around with the form. So there is a sort of a critique to this fake freedom that was propagated back then, and on the other side, it's a positive message, because basically what we say with this project, or nowadays it's not so relevant anymore, but back then it was really important to state this, was that using parametric design, computational design, doesn't mean to lose control on things. You just move, your let's say control to another level, and maybe this is then also, I'm going back to what Gilles showed before, it's a control at the larger scale and another order of magnitude than the single object, and the single surface and the single detail. So give it away in order to get more control on things. Now, a second, I would like to very quickly, this is probably pretty didactic, but I think it's important because there's a lot of confusion on these things. Why should we code as architect? And this is also the question of the high tech. There are things where we cannot do without the high tech, but we have always to keep in mind or to ask ourselves: is what we're doing needing high tech, or is it what we're doing needing coding? Because coding is not an easy thing. It's very time consuming. It's a stupid thing at the end if you don't have a clear target. And to do this, I show an old house that we designed probably 15 years ago. You see, I'll show it closer. It's nearby a lake in a wonderful setting, a village with a lot of constraints, formal constraints. I'll only show you two aspects of this. One is the volume, so the shape. It looks a bit strange, so a rectangle, it's a pretty big thing with two cuts. If I show you how they are generated, you immediately understand, just out of your own practice or thinking, how simple these things are. So it's two stories. First one is the client builds his own garden. Happens, and the garden is in front of the lake. So if you build a new building, then you want to make sure that the old building still has a relationship to the view to the lake. And then you have an angle, and this is a number, and depending on how big the number is, the ratio between view from the old new house plus difficulties in arranging the floor plan of the new house. So there is many implications. The second cut is much more rational. It's just if you wanted to drive a car in the back of this house because you don't want it in the front, then you need to take away a bit of house. Here there is not much negotiation. Maybe if you have a big SUV or a small car, you could play a bit with this angle, but it's reasonable. Okay. Why I'm showing this? I'm showing this because this is a classical problem that you could very easily program. So you could write software for it, that simulates everything and does nice diagrams, many colors, whatever. Then you could show it to the client, but nobody does it, and we didn't too, just because this problem is simple enough in its consequences that you can iterate through it as architect, as human, while discussing, while sketching. And this is why you do not program. So you don't use high-tech to solve this, but it's a high-tech problem. So there is no big difference to a more complex one. I will show you the more complex problem that the first sight is also very banal. This is just the floor plan of the ground floor. It's an open plan with a core. The core carries pitched roof, cantilevering on 4 sides. And the pretty specific thing is that we have a ribbon window that follows this roof. It's a super simple geometry, apparently. Now, what you see here, these lines, this is timber slats, vertical ones, that are used to hide all this glass, because of the building code. The building code doesn't allow you any glass, and this is a trick just to pretend that this house is a timber house. It works legally. It works perfectly, because as soon as you have an angle, a minimal angle, it just closes. And if you're close to this membrane, so in the inside with the contrast and so on, it disappears. Now, if you look at the right side, you'll find out that there is something strange with these slats. They are not regular, but this drawing shows it nicely. They are carved out on both sides symmetrically at certain position for a certain height. And here on the bottom, you also see there is, so this cut can be tilted. And what this produces is nothing else than an engine that allows you, when designing, to create. So if you assume that you have glass, transparency, and then you put a screen in front of it, with this operation, you are able to create sort of lenses. So areas where it becomes much more transparent. You are able to direct, your opening by tilting. So you could have a preferred side. And this is the thing that allows you to, do what architecture has always been about. Transparency, directing the field of view, closing up because of privacy or because of overheating or whatever. So it's sort of a modulated surface. The only problem is that we have, even though it's a small house, it's not a big museum, but still we have 315 parts. And these 315 parts are, because of the stupid geometry of this house, that is not just a box with one window. They're all extremely different. Here you see just the development of the thing. And 315, it's nothing. Imagine it's nothing. But if you consider designing, by designing I mean to modeling geometrically, I can do this on paper or on a computer, doesn't matter so much, 315 parts that relate to each other, you'll find, and that architecture is about iteration. So you do something in order to test it. You draw it or you build it in order to find out if it's good and to find out where you should eventually move. Then it is not going to work. But if you parameterize it, and this is programming, if you say this simple logic, is formalized in a piece of code, that allows you to instrumentalize a computer that, can go through this 315 parts for a computer, even for a smartphone nowadays, this is just nothing, then you are able to control this whole thing. So the same thing that before was, a simple iteration between one number and a consequence, here is also feasible. And then the second thing, once you have done this step to use high tech, so you don't draw it, you program it, then you have automatically produced data. And if you have produced data in analogy to the mill and the table that I've shown you before, then you can use a machine like this one, for example, to produce these 300 very different, very specific parts automatically. And this now is very important, because if you would have 315 drawing and would you go to a contractor, you would just get a high price for it, probably, because it's not, what they do every day. The logistics behind it's all a bit messy. But this machine here is a machine the contractor would anyway use for the 315 parts, even if you don't ask for. Because as soon as you say, I want them flat, flush, and I want them, 22.5 centimeters, and he has 25, then he puts each part on this machine, runs through, tilts it, turns it 180 degrees and runs back, So by doing this here, we didn't add €1 to the project. We were just adding data. Okay. And this is the result. Sort of a minimal intervention on these physical parts that often is not even visible. Sometimes it becomes dramatic and its consequences depending on where you are. And this is an important part. It comes for free, but it doesn't come for free just by chance. It comes for free if you are designing the whole process. And then many questions become relevant. So, did you first find the machine and then derive the design from this true operation the machine is good at? Or did you start with the design and then you were very, very lucky because you went out there and said, wow, this machine matches, These are tricky things. But it's all about, new ways, or sometimes I also think they're not so new, they are new now in relation to technology. Ways to relate design to our activity that goes beyond, defining the definition of form, being it functional or arbitrary. I don't care so much, and extending this into the realm of the physical, And there it's where in our work at a certain point the robot came into the picture. And the robot is of course the champion of automation per definition. It's a provocation on its own. For a long time, if you were showing this machine, now it's a bit better because there are many, the discourse about automation has broadened a bit, but for a long time showing this machine, the first question after the lecture was, and what about labor? This very, justified and legitimate, but very, deeply sitting reactions, triggers, as soon as you show this. Because this is high tech, although it's not so much high tech. We started with this 2005, and this machine then was already a commodity, a mass product, cheap mass product compared to the two machines you have seen before are more expensive than this robot, because this has been produced in millions of pieces. Okay. This, by the way, is an artist image. It's not the way you use a robot. But we use it because it very nicely shows that, at least for us, this machine always, engages a dialogue with us at different levels, as craftsman, as a designer, as clients, But the machine is not autonomous. Doesn't make sense, So there is this mutual, and this is a mutual dependency. This is also a nice and important thing. And maybe now to clarify a bit this, I'll do a few didactic slides on, notations. This is, let's say, the goal. Let's assume that this is the goal, a banal brick wall with banal bricks. Another question is, how do we think of this brick wall, or how do we represent it? How do we communicate? And this could be one answer. Probably the first, if you are asked, the first instinctive way of depicting it would be just to draw it. But this is extremely inefficient. In reality, since ever, the way we think about the brick wall, it's a very, very complex thing, is with this cultural technological convention. So at a certain point we agreed that there is something like a bond, You know, and in every language you have, you know, the corresponding, and the bond is nothing else than a thing describing the steps needed to perform it. So it's a process description, if you want, and this allows us, first of all, to communicate across professional borders. So everybody that knows what the stretcher bond is immediately understands. And then this allows us to compress down the information needed for all the rest. You know, if you look at this, you know, here, to basically the size of the element, of the standardized element, or the type. You know, I think of your, Gilles, you know, this is, you know, the element. There is no discussion there. And a few measures, a few additional numbers. In case of the brick wall we have seen a bit in the beginning, it's clearly a length and a height, not much more. And then there are a few additional things, I know, but I mean, it boils down to this. Now, if we work with a computer and a robot, so with technology, then it doesn't make sense to explain to a robot, to a computer, what a stretcher bond is. You know, this would be a strange detour. But we just write it like this, because this is the way you describe this. You know, and I'm using this example, of course, because it's so banal, it's so simple. You know, there is nothing simpler than this. Two loops nested one into each other just produces this wall. You know, and if you do more complex three-dimensional things, then it gets way more complex. But in order to talk about it, it's a good example. So this is producing exactly this, and this is uninteresting so far. You know, because it doesn't produce anything new. Now, where we got excited, this was a few months after getting this robot, when we said, okay, let's start with bricks. You know, we don't have the time to you know, to now, or it's not efficient now to reinvent processes. Let's just check what we could do with this machine that is able to automatically place parts in space with the oldest standardized part of architecture. And now you see here a human, this was a student, checking what else could happen in such a bond, you know. And he tries to rotate these parts, tries to understand, you know, what are the tolerances, how much can I turn them, rotate them until they fall down, cantilevering and so on. And then he decides to add these two lines of code at the very end. So only the pink has changed here. You know, this is exactly the same. And from the variable names, you understand it's about rotations. And it's not important now to understand what he does. He does exactly the only thing what is important that now he applies he modifies the position of each single brick. So there is no rule anymore from this point on. So the code is here. This I can read, I can change. This is operational, and this is just data. It's a mess, you know. But now this is a mess for us humans. You know, because this I cannot give anybody. I cannot draw. I cannot give the list. You know, so this beauty of the stretcher bond as a cultural convention allows us to make sure that we get what we want. Here fails, but it doesn't fail with a machine. In the contrary, the machine is expecting this, and the machine would have huge problems with any other notation. You know, and this allows us to directly connect the power of design, and when I say power of design, I think you know, the conceptual level, the operational level that includes high tech when you program. So this is a new part of our profession, a new skill, directly with a physical output that is taken care of a machine that doesn't care, you know, if this wall is regular or not. We are again at the previous example. It comes exactly for the same cost. As soon as this process is set up, there is no cost different. And this is fascinating, because suddenly you end up with something like this. And this is where, for us, this term of digital materiality started to make sense. And I think that is extremely physical. is also scaleless to a certain extent. You know, it's about material, but also, you know, relationship of volume, voids, light, you know, and it's completely malleable at the same time. It's not a result of a super expensive, super complex, super luxury. You know, it's the simple thing you can get if you engage with such a thinking and with such a project process. Now I would like to go through 2 real-world applications. This is a winery. I'll show it because it's interesting, because we have another winery that I'll show later. I like to show the relationship between those 2 things. This is the way we designed it. I cannot now explain in detail, but if you have the freedom to freely place 10, 20, 30, 50, 100,000 single parts, then the question, how do you turn them, becomes pretty relevant. So you need a strategy to inform it, to produce the data. This was pretty banal, straightforward. We filled the building that, by the way, was given to us, was an objet trouvé, not designed by us. We filled it with spheres, did the dense packing, looked at it, transferred the color information to the rotation, ended up with this. And then implemented the process. Pretty easy, you just need a gripper. And everything else is pure information. So the knowing how the glue has to be applied, and then the final positioning is super simple for the robot. It's all again automatically, derived from this terrible large amount of rotation and numbers that give us a headache, but not the machine. And so we were able to just print these walls by additively placing elements. And I'm, consciously talking about 3D printing because for us, back then 3D printing was not really there yet. There were a few pioneers, but we felt that, to 3D print architecture would not be adequate, because 3D printing has been there since day one, But the elements, have a certain size and a certain logic, and it's not by chance that the brick is what it is, And if you say the brick becomes microscopic and you want to have control on its placement, then you just blow up time and costs. And then we started to think about this relationship between the size of the parts and in our case, the robot. Yeah. Here you see few images. You see what it does then to architecture. Always keep in mind that there is no difference to any other pattern, or even if you would do it completely flat, regular, a pure stretcher, you would use the same amount of bricks, the same amount of time, the same amount of energy, and so on and so forth. Second one is a bit more complex, also because it scales up the number of parts, and here the number of parts become custom, although in a very, very controlled manner. This is 50,000 parts, timber parts, flats, 5 by 10 centimeter, so pretty fragile thing, aggregated to one 2,300 square meter roof, structural roof. And it's not only 50,000 parts, it's also almost 1 million nails. So it's a pretty brutal, simple way to aggregate this thing. And what you see here, why this drawing is interesting and important, and by the way, it's probably the only drawing that exists from this project, because drawing were useless. There was only data. But what it expressed very nicely is that these parts, the symbol part, at this resolution, may turn the whole thing into almost a fabric, becomes textile. It's where as long as there is a computational relationship, a relationship between these parts, then you can, for example, there we had, it's always the same thing. At the very end, you find out that you need ducts, you know. You had them in the project for the staircase for smoke evacuation. You had them in the project, but they were always too small. Then at a certain point, they come, the engineers say, oh, need to be 3 times bigger, and then they don't fit anymore. And then normally you would just cut out, you know, and do some fixes. And here we just stretch, because as long as it's not built, it's completely malleable. We just stretch the thing. Because the system behind is extremely straightforward. You know, it's just this big, long 15-meter trusses, you know, and the only thing that changes is the relative length and the angle on the end cuts of all these subcomponents. Yeah. And then we go we zoom in another step, then we have 1 million nails. Again, they all have their own position because there are so many dependencies. So I think that you can forget about, you know, designing and standardizing. So there is not one fits it all here. But it doesn't matter, because as long as it's computationally described, then you don't care. Yeah. Here you see again how simple then the fabrication of such a thing is in reality. You know, just this is the brick we had before, and now we just cut its ends, so we can have a bit longer and a bit shorter bricks. This goes onto the table. This just now is a very large table, and this huge robot, you know, places the parts, and after a single part has been placed, now one first nail is shot in order to keep it in place, but then it turns the aggregate, the end effector, and, you know, brings the rest. Yeah. And these huge parts, custom parts, are then installed, so completed with all the subsystems, sprinkler, electricity, light, and so on and so forth. This is the classical, you know, processes of prefabrication, all in the shop, and then they are trucked onto on the building site and installed there. And what is impressive and important is that you start from 50,000 parts, and without any human intervention, you boil them down to 168 parts. This is one part. There are 168 of them, and they just picked up, craned in position, and fixed with 5 screws. No? And this is not exaggerated, because they have just their place, they fit. You know, and this is, if one end is crazy complex, imagine 50,000 different parts in a room. This is banal. Here you cannot just nothing can happen. Yeah, and you end up with this. This is nice because it's our institute building. We were actually allowed to integrate research in a project the university would have built anyway, what is a very good thing. Yeah. Now I wanted to do one step forward and introduce 2 projects that are pretty recent and that work with augmented reality. And we started with one timber project, where again we have parts, and these parts are all identical. And the project is about a wall, an acoustical diffusive wall. I don't explain how this works. This is complicated, not the point here. But the building system is what you actually see here. So you have parts, and these parts need to find their position. Now, this is exactly what 10 years ago we used a robot for. You know? because it's just about, this is always same element rotated. You have 4 possible positions, and then you have, a Z translation. This is exactly this data that back then only the robot was able to manage, but with augmented reality, we can make this thing extremely more flexible, because now, just these very simple relative operations of parts here, that are prefabricated in large amounts, can be very quickly and very easily placed at their final position in space relative to each other. So here we can transit from this just abstract bunch of data to this very precise and organized wall with these simple tools, They are basically, we'll see it in the next project. Basically, it's a camera and a display that tells the person where he is in space. A few images of this thing. Yeah, and now this is a second winery, and this is a very funny story because we were approached 3 years ago, before the pandemic, by people that were also producing wine, and they were also like the first one, Gantenwein. There were so many similarity. There were people that came from another profession, decided to invest in in a winery, God knows why, and so on. And they knew that we did the last one, and so they asked us, could you do the same thing for us in Greece? And we pretty instinctively said, no, we will not, because there is no point in doing it. We have done it, and it was after the financial crisis. It felt really odd, to bring robotically fabricated brick elements down to Greece in order to install them there. Why? But they came back to us a few times and obliged us to think, okay, what is the problem? What is the difference? And then we decide, okay, we do it, we redo the project, but we radically change the premises. So we do it with local labor, with local material, with augmented reality. And here you see how this worked. And it is very nice because, while the first winery was reduced to the max because we're not able to use mortar. We had to use glue, and this was all a bit an ugly thing. Here, thanks to the dexterity and the craft of these people, that do everything. They do extremely fast, extremely efficiently. They even have fun doing it. The only thing they don't know is where the part goes. And here with this system, we allowed them, because the first placement is pretty intuitive, but then in order to understand, how to move it on the last 5 millimeters, this system becomes essential. I'll show us a short movie. Some active process. And the nice thing is also that this also was an objet trouvé. This is not planned by us. This was a ruin of the financial crisis. So basically they started to do something with an engineer, then they ran out of money. The whole thing stayed like this for a certain amount of year, and then they restarted. So it was about intervening with custom brick element in an existing frame. And here you see how much, super complex operations are involved, in the production of such a thing. And I can tell you, we work on the automation of processes with robots since 15 years. This is crazy complex what is done here. And now, of course, this has many, many implications, because it could now look like this would fundamentally question everything we have done before. This would be one way to read it, you know. Or it could mean that by following, you know, because this is not just going back to something, this is going radically forward, because when we started this, the possibility to track something in space at this precision was not even thinkable, you know, not even with a lot of money. You know. Now this thing become accessible. You know. And for us, what it means is that by, again, going even more high-tech, we are able to integrate many more things than before. Before it was a pretty, you know, dry, closed, locked system. You know. And at every edge you were running to a problem that would cost another 200,000 to automate, even not being so interesting, but necessary. You know, because without this investment, the whole thing would just collapse, not work. And if you're able to fluently integrate everything, you know, information, craft, robots, robots that understand that you're around, so they ideally don't kill you, you know, this suddenly becomes 3,000 times more powerful, you know. And then these visions we had 15 years ago, where with time, by understanding how complex these things really are, you know, started to you know, make us concerned, you know, about how many 100 years this would become reality. Now suddenly have become much closer. You know, now suddenly these things are thinkable. Yeah. Okay, now the last few minutes I would like to just go through. Here I'll change a bit track. So far we have talked about very standardized, very familiar materials, processed in very simple ways, and the question was on how do we place them in space in an efficient, meaningful, rational way by using whatever means. Now I would like to go into materials. Was here, yeah, material processes and self-formation, and because these two things relate at a certain level, they have a relation to each other. But in order to explain what I mean, I'll show just two projects. You know, and this now is really, we call it research, but it's probably more than research. We always start with an installation. We always start with something that we haven't understood yet. Just try to do it brute force. See where the limits are by putting a lot of work and risk and so on. And then in a second round, we go after it in a more systematic way. You know. And this is a project that builds on the physical phenomena of jamming that is described, this depicts it a bit. It's described that what happens to rigid bodies if they are constrained by limits or by forces. And if under certain conditions they jam, and that means that the single parts are locked. They're not able to go anywhere anymore. So it becomes, the whole thing becomes rigid. And the nice thing, or the very specific, wonderful thing that distinguishes from many other ways you could, produce rigid parts by introducing glues or mortars or whatever, is that the jamming transition can be completely reversed without any degradation of anything. You know, and this can go back and forth an infinite amount of times. It's not limited, but it's very much related to form. To understand this, this is what we have done. You know, you can have a tube and then fill it with whatever you have at hand, and find out that with spheres it doesn't work at all, and cornflakes are perfect. You know, they have the right form for it. Okay, and with this, we did an installation. We're asked to do a piece for the Chicago Biennale. And we decided to provoke the jamming effect by introducing just very common recycled string in layers. And this now looks very simple. We went through hundreds of tests with different configuration materials and so on. But at a certain point, we found out if we do layers and then we have this string, the string doesn't even need to be strong, because it's not really it's not a reinforcement. It's just making sure that these rigid parts cannot, leave the surface, and there is no chain reaction. So there is friction, but a minimal one. And as long as the whole thing stays together, then it can really carry interesting loads. See, this was filled, and now it gets demolded, and material starts to collapse because this physical limit is not there anymore. And then you can, you have to create this chain reactions. So you brush it a bit, and the brushing works until you have reached the string. The string is the interface between, what is sort of solid and what is, just. And this was then the piece we showed. So the direct sort of manifestation of this project, you introduce a form with a robot through a string in a formwork, then you demold it, and then you leave just the material where it was. Yeah. And it's a very, very interesting materiality because it's extremely strong, it's extremely robust, resilient, It can reassess. If you move this thing, you'll find a new equilibrium. At the same time, it's extremely fragile. For example, by beating it, you cannot really harm it. But by brushing it, you can slowly destroy it, because you get these pieces out. And then it has this fantastic property of being fully reversible. And this is probably now... this is what architecture has to become, an aggregation of parts that can be rearranged an infinite amount of times, This now is a very, of course, beautiful, poetic way to disassemble, because it's sort of like rewinding the movie of the construction, but it's not, it's just rewinding or winding up the string. But beyond this nice poetic implication, the real message is, how do we manage to do this in architecture? So to get rid of all this, thousands of kilometers of ugly tapes, that are, needed everywhere. And this project doesn't have an answer to it, but it's asking the question. And then, of course, second step was with a PhD student to really go after it and find ways to automate this and measure its performance, and ended up with a very nice pavilion that then was also loaded with a really heavy steel plate, a recycled one, 9 tons, in order to give it this weight that is needed for the whole thing to be stable. Yeah. Okay, this was the jamming project, and at the end, last topic is I go back to bricks, but I change material. This now is clay. It's not burned anymore, and what interests us is that this material. Here you see it. So this is the raw material. And this is once it's processed and extruded, that these parts, in this case, the cylinders that we use for these projects, for a pretty long time, they can be deformed, because you don't burn them. Then if you depending on where and when you process them, you can do incredible things that you cannot do with real bricks, because if you do these things that I show you in a second with real bricks, then you just create trash. The project is about this. It's about Yeah, it's sort of a counter thesis to the 3D printer. Even the 3D printer we have seen today, WASP. The printer is bigger than the building, and this at a certain point creates a problem, a logistical problem, a physical problem, and so on, a structural problem. We said, what if we could shoot these parts through space at the right position? And there, of course, there is a great deal of naiveness in such an assumption, because there are 1,000 reasons why this doesn't work. But then our technique in such cases is to really try to find solutions. First thing you find is that the problem is not that new. Ballistic curve, everybody knows it. At the same time, everybody knows that this doesn't really work. This is a nice simplification, but in reality you have so many disturbing things, like the fact that these parts are not all the same weight and there is wind and whatever, that you need something like this. So you need a feedback system, you need a device, in our case a scanner, but in military technology this is known since hundreds of years. So if you want to shoot something somewhere, you need somebody observing it and then giving feedback. It was too long, too short. This is exactly the same. It's just a closed loop, without humans involved, where when a part, so this is the scanner, when a part lands, the whole system gets a feedback if the calibration of the system was good or not. And if the system observes failure, the system starts to adjust this parameter. For example, the angle of shooting or the force, the kinetic force that was given to the part. So this machine is extremely simple. It's just a piston that is oriented by a robot. It allows to shoot through the air these parts that at the beginning are platonic bodies, cylinders, but when they impact, they do two things. First, they close the gaps. If I have a brick and I build something, then I need something to close around. And if the speed in which it's landing is big enough, then these materials, will really, I don't know how to say in English, they will create a homogeneous whole, so you don't have a cold joint anymore in between. So if you cut up one of these things, you find. And the third thing that is for us fundamental is create a completely new aesthetic, where it's not so much about control, precise control. It's not about the pattern, but it's much more about the dynamics. It's about still being able to read in this homogeneous material that is actually, vertical. It's a wall. For example, from where did the part come from? Because the deformation of the part tells this story. This is a nice thing, just to close, to show how out of control this thing is. So now, if you would go after this, just with technology, trying to find a way to control it, you would fail. It's impossible. So this system tells you that you have to sort of liberate yourself, and let this thing just be what they are, and to concentrate on the most important thing. The most important thing is that this thing, grows vertically, that you can control its geometry. This is the last project that builds on this first one. The first one was again an art performance. There was no scientific proposal or PhD, whatever. It was just fun, but it helped us build up the case for this second project, where we have 3 PhDs, one with us and 2 other in material science and robotics, where we want to do the same thing, but in a more controlled way. And what you see here is just the brief. So we needed to go up 5 meters. And in order to, the engineer said, if you want to do this with this material, all the things, the unknown we have, then we need 1.25 meters at the base. And then you think it through and you find out will never work. Takes us half a year to build this. It's way too much material. Then we said, okay, we'll go up with 15 centimeter. Then you have to find a strategy. And then it's where you need the control, because you know how the shape should be if you wanted to do it with 15 centimeter. This is not it's no rocket science. It's no magic. It's just simple things that you can test with paper. But to do a thing like this then becomes, of course, very demanding. And with this last video, now this is the sort of simplified version of it, where you have now a robot that doesn't, throw it through the air, but that, presses these malleable bricks one into the other. And again, here it's both. It's the dream of automation, because if we could think this at large scale and, most important, at high frequency, because there is no reason why this is so, boring, slow. This could be 10 per second, 20 per second, but still under full control of the mechanical properties and these things. Departing from one standardized part that is placed in space in a custom way, and then also by let's say the ability of this brick here to deform, it's a gigantic advantage for the whole system, because a thing that can deform cannot have a collision. And in automation, often it's the small collisions, 1 millimeter, that makes your life really hard. Yeah. Okay, I think this was the lecture. I don't know how we don't have time. I guess we run out of time, right? Yeah. Or we do it. Is there a panel at the very end? No. Okay. So then, questions, please. There.
Thank you. First of all, I don't know how I'm going to concentrate on my own lecture.
I had the same problem.
My brain is full of
it,
stuff
it
now.
Works.
I want to ask you about the size of pieces. You briefly mentioned that the size of pieces of the elements that we use now has to be rethought, because the pieces before, they had their own logic. It's a logic that came out of the needs of human hands and human legs and people on scaffolding. And now the context is different. And I started thinking when you mentioned this, and then as you moved on through the projects, I could not stop thinking about it. For example, this amazing shooting clay thing. Maybe it shoots pellets of clay, which is something that would be impossible otherwise, a clay machine gun. Or with the wood, the roof of the research center in ETH, going smaller and smaller, I guess, allows us to use pieces of wood that would otherwise be useless when you want to make such large structural beams. So I want to hear a bit more about the question of size, because it's leaving the realm of human hands now, and there are so many possibilities, I guess.
Yeah, it's a thing we question since the very beginning, because in the very first decision to do this proof of concept of the choice of the machine with bricks, the question about if a brick is adequate for robotic construction was already inscribed, And I must say that our first intuition back then was that probably the robot being bigger could just handle bigger parts, and so it would be very reasonable to have just bigger bricks. But then very quickly we found out that it's not such a simple equation. In some situation it is very true, but there are other ends in architecture where then this becomes too low resolution, where you run into problems, and this is why we never, we always discuss if something is reasonable or not. There is part of the discussion that is depending on the processes we use. So we find out that we cannot shoot pellet at this speed, then we just, do work with bigger parts, because we don't want that with a theoretical process that, but it's a thing that we have to reconsider each single time. And also technology develops things that are very inefficient, suddenly become efficient because a new mechanism or is created, or a new material system is suddenly available. For example, the nice thing with the jamming thing is suddenly we found out that there we don't need to place each single brick stone, what would be a madness, would radically question the feasibility, and would make clearly this whole thing too high resolution, because if you want to place them single you need at least this size, but they find their position on their own. So you place another information, with the robot, which is the string, that make sure that this thing jam at the right part. So I think it's a very important question, but it doesn't have one simple answer. And I think this is also very attractive because this asks us with each new material system or project to evaluate, what is the right answer inside this sort of toolbox we have created.
Yeah, the back.
Thank you, Fabio, for one wonderful lecture. My question is mostly motivated by the first part of your presentation, where you highlighted a series of skills that seems to be drawing the set of skills that architects today must have. And because I think also you should have some students here. Could you share a little bit about how in Zurich students are being introduced to these technologies, to these methodologies? Is something that is happening in the curriculum, in the undergraduate curriculum, or is something that is happening, let's say, through the involvement with your research group? How, let's say, students and future architects are being introduced to this?
It's a perfect question, because until now they are not introduced at all. What sounds strange, but it's like this, at least at the bachelor-master level. This has many historic reasons rooted in the school, but also in our own research practice that until now has been very, very research oriented, also from the financing scheme and so on. But right now, Matthias and myself are moving our practice at ETH radically into teaching. I think that for a long time, probably for too long, we didn't really recognize as being fundamental, because it's super satisfying and inspiring to work with PhD students that have 3 years to do creative stuff, and then the question is, if I have a student that has 2 hours a week, on 13 weeks, and has so many other problems, to how I'm gonna engage, these young future architects. But this is exactly the important question, because if we are not able to create a culture that is, playful, that is, not driven by productivity or, by the fear to be excluded by some BIM community, all these things, because it creates a counter reaction with architects. So we have to make sure that these things become part of just a repertoire of design practice, And there it's got much easier now with visual programming interfaces like Grasshopper, you know, that allow to do pretty complex things without, you know, going through this brutal learning curve of, you know, programming, written programming. But it's just now it's an intention. We know that it's important, but we will see in 2 years how we do exactly and what success we will have. You know. The question, the answer is just to, so it cannot become a specialist job. If we turn this into a specialist job, then we have lost. You know, then we have the boutique architects, you know, and some engineers, whoever doing the other 99.9%, you know. But it's absolutely uninteresting, you know, meaningless. Yeah.
So, any more questions? No? So we move on to Aris. I will present you first. Thank you.